because it is a chemistry class, in general, the best place to start would be with a chemical reaction. It's not a requirement, but it's usually a good idea. Okay, so if we go through and look at this, 18 grams of rust produced, so that's given us some context here. We're looking at a reaction where we have produced rust. Okay, when a 2 gram sample of iron, so iron would be Fe, and oxygen gas, O2. Okay, react in a combination reaction. Well, heck, there's a combination reaction. I have 2 reactants and I've made a product. So I've now pulled that information out of the question. Rust, iron, oxygen gas, and that it's a combination. Okay, that information is really what's going to kind of drive the solve for this. I could go through and add a little bit more information just because I've got a picture. I could start to layer that in. I know that the rust that I've got is 18.0 grams. I know that the iron I've got is 20.0 grams. And I know that the oxygen I've got is 8.59 grams. Okay? Then the question itself says, what is the percent yield of rust? Okay, well, percent yield. One of the things that might make this question extra challenging is that and then Victor, I don't know that I actually solved this one all the way out. It's not a combustion, it's a combination. And the combination part's going to become relevant in a little bit. And it's what's allowing kind of the fast solve on this. You're being asked for a percent yield. The percent yield makes this more challenging because the percent yield aspect of this question is the very end of this unit. That is a formula that is actual over theoretical. Okay. So if we're going through and looking at our context, we would need to be able to kind of substitute information in here. So the actual is what we actually obtained in the course of running this experiment. Okay. Well, the actual yield of what? Well, the question told us we wanted of rust. Okay, so what did I actually obtain? Do I know what I actually obtained? Yeah, it said I actually got 18 grams of rust. Okay, so the actual yield is given to me directly in the question. It's 18.0 grams of rust. The real issue becomes now the theoretical. And when we talk about percent yield, we address the theoretical as a calculation. And it's going to be a calculation here too. But it's the question of the amount of calculation that you have to go through and do. Okay? In the context of when we talk about percent yield, the theoretical calculation is done in a limiting reactant type situation. Okay? To do a limiting reactant type situation, you have to have a balanced chemical reaction. So this theoretical yield could be done using a balanced chemical equation. To have a balanced chemical equation, we have to know the identity of all of our reactants and our product. Do we know the chemical identity of our product? We know it's a combination reaction where iron and oxygen have to somehow combine. Okay? But the question becomes, do we know what ratio they combine in? You are not required to understand or memorize the charge for iron. Why not? It has tons of possible charges. If we don't know the charge on the iron, we can't determine the ratio of X and Y. If we don't know the ratio of X and Y, we don't have a balanced chemical equation. And this is usually the hole that tutors fall down. Because what tutors will go through and do is that they will decide that rust is FeO. Or they will decide that is Fe2O3. As soon as they've made that decision, they're now making an assumption on the question that the question has not provided. Okay, and that's where they go wrong. Okay, because we don't have that balanced chemical equation and we don't know the exact ratio of iron and oxygen in rust, that method does not work. So how do we get the theoretical then? Okay, well, is there anything else that we could pull from to get our theoretical? Okay, well, one of the things that I referenced that was kind of important is that it's a combination reaction. Why is it important to know that it's a combination reaction? Well, the general form of a combination, A plus B equals A and B. If I give you 1 gram of A and 2 grams of B, how much AB did you make? According to the law of conservation of mass, I made 3 grams. I cannot create nor destroy matter, which means I know the mass of the product produced. How is that relevant here? The 18 grams is what I could have actually made. The theoretical amount would be the sum of these two. Okay? The reason I can do that is the law of conservation of mass. Okay? So what do? I take 18 grams and I divide it by the sum of 20.0 plus 8.59. Now I multiply by 100 and I get my answer. Okay? So it's actually a pretty straightforward question. There's a lot of information written up there. Okay, but what I'm going to do is delete the stuff that we didn't have to go through and write. The majority of what's written there was stuff that was already stated explicitly in the question. All we have to do is recognize why we're allowed to add those two numbers together, which is actually one of the reasons why I like this question a lot. It's a really simple application of the law of conservation of mass that stacks with percent yield. The reason I don't like it is that it stumps people that know what's going on, and people that don't know what's going on just jam numbers together until it works. And so usually they stumble across just adding those two numbers together, the 20 and the 8.59, and then just doing a division and being like, oh, well, that's one of the answers. Okay, so I like it a lot because of kind of the simplicity behind it, but to the same end, the simplicity behind it makes it easy to effectively guess your way through it. If you just randomly mash numbers together, you will notice that the multiple choice answers that are listed there, virtually every single one of them has some route back to just mashing numbers together. So you kind of have to sort of luck into that process. It's not just a complete blind luck, but I've gotten a lot of feedback from students being, well, I just kind of guessed. Your intuition on guessing was really good. And yeah, typically it is that just people are overthinking it. For the record, I did actually record that. I do apologize, Bree. I did forget to record your intro into the lab. But this one is recorded. I will post it to the WebEx meeting as soon as I've got it recorded officially. So for our lab, when you go to lab, you should be getting this kind of screen, or see this screen when you first start into it. It gives you kind of a directions on what's happening for the rest of the semester. It gives you a couple warnings here that you are forced to move through the modules in sequence. And that's an attempt to slow you down and prevent accidental skipping around. Because this lab sequence does match fairly well the lecture delivery. If we look at it, which I didn't say before, the first two labs are exam 3. The last two labs would show up in the final. Okay? So that is kind of an important distinction to throw in there. So it tells us to go to the modules. So if we go to the module, It should be the very first module, and you should notice virtually everything is grayed out except for the very first thing. You'll also notice that at the top right, it asks for you to complete all items. So there's a bunch of kind of random things. So grays meaning you can't look at it. Only one thing is active. It tells you kind of instructions. You need to complete all of these items. And then if you look, you see these kind of circles. Those circles will signify that you have done that part of it. Okay. At this point, we haven't done any of it because this is a brand new student in it. So, yeah. So to go through and complete, underneath each of them, you'll see a little bit of text, and that text is telling you what you need to do. I believe the vast majority of them, I needed to scroll and check, are just views. The other ones are then submits, and those are the actual submission of the lab itself, of the lab document. Okay. The very first one is a mark as done, and that does seem to be the most difficult for people to go through and track. You'll notice it's the same page that you went through and saw already. To acknowledge that you've done it, you have to go to the upper right-hand corner where it says mark as done. Depending on the device you're looking at, that mark as done might be at the bottom. I honestly don't know, and I might be able to check it. Nope, it looks like the mark as done is going to stay, okay, in the upper right. Sorry for the screen shifting. So, since we already read it, we can click as mark as done. When we click next, now it will let me advance, okay? Because these are now just views, I can now continue to click next and move through it. My recommendation is that what you do is download this document. What this document is the lab background information. Okay, that's all of this stuff. For whatever reason, the people that put this together decided to not remove the procedure. So the procedure is all there also. You're not doing anything with the procedure. Okay, so you're just kind of reading through all that. And then you get to the lab report. Okay, and the lab report is the meat of the assignment. Okay, this particular lab report is a little bit more challenging, but is based off of this YouTube video. Okay, so if you've downloaded this as a document, you can click next, and the very next thing in your next screen, which I'll show you, is the video. Okay, so it'll take you directly to that video. If we click next again, because it will let us advance, okay, it's going to now take us to the PDF. So if for whatever reason the doc didn't work, you can now access the PDF. And then you could take a quiz. Okay, the quiz is on the lab. In theory, this quiz was a pre-lab. I decided to place it at the end so that you could have gone through and effectively figured out all of your answers potentially first, and then there's your quiz. You only get one chance to go through and submit it. You are expected to have reviewed safety documentation for the individual chemicals. There is no time limit. So what you could go through and do, because you don't know what that safety is have the safety open to the side. And if you encounter a question about safety, just go look it up. Okay? Since there's no time limit, you don't have to have that handy. Once you've taken it and submitted it, then you'll be able to move on to the next part of the assignment. If we try and click next now, it will allow me to advance, but it just says that it hasn't been unlocked yet. Okay? And what this is the actual submission of the assignment. You have to submit the assignment. But the only way that you can get to it is if you've done the quiz. Okay? You must submit the previous assignment. That's the locking in sequence. Okay? So if we backtrack, this was probably the worst way to backtrack it, but we're doing it anyway. I can do it with the PDF. Cool. So PDF, sorry, all the scrolling, and we get down to our data tables. Uncertainty. The uncertainty would make a lot more sense if you were in lab, because you would be able to read the balance, because you can't see the balance in the videos, or so I am told. That's going to be hard to actually see what the uncertainty is for them. So I will refresh your memory from our very first lab where we talked about the precision of devices. It's the plus minus. on an individual balance, the uncertainty is the last decimal place, and it is usually specified as a 1, 2, 3, 5, or 7. Okay? The most common are the 1, 3, and 5 that I've seen. Because we don't know, what we're going to do is go ahead and guess. So we're going to reference that last decimal place, 1, 2, 3, it's the fourth, that needs to be a 1. Okay? The rest of those places are going to be zeros. Okay? And that's what we did in the uncertainty lab. Okay? So that's just the uncertainty of that device. All of these measurements are masses, so they're the same. For my lab, you could just, and actually don't do it that way, you could just do quotes, because we're just copying from the previous one. If you aren't in my lab, I would check with your instructor. It's not that much effort. You could just rewrite the numbers. Okay? Then the next part that becomes a challenge is trying to fill in, please reconnect. So my Wi-Fi is having a bit of a problem, so I'll just keep talking. Is those bottom 4 boxes. Okay. The uncertainty is still a copy down, so you don't need to worry about that. But the next big one is going to be, what do we put in for these? Okay. Those, you're actually being told what to do. That is a mathematical operation in the parentheses. That's saying take box A. Let's do it this way. That's saying take box A and subtract box D. Well, box A was the mass of copper before the reaction. Box D is the mass of copper after the reaction. So the difference in those two would be the mass of copper that reacted. So we would write down whatever that number is. I'm going to ballpark it 1303, I think. Close enough. And then the mass of the silver is E minus C. So there's E minus C. So we'd now do that mass. And again, 4211. And I'm pretty sure I did that one wrong too. But those would be the numbers we'd be writing in there. We're just doing that subtraction. Okay. That's now the bulk kind of collection of the data. Where we are going to be spending most of our time is taking that blue number and that green number and changing them into something useful. Because right now, those are grams of copper and grams of silver. Okay, I can't make comparisons between those, because to make a comparison, I would need to go through a chemical equation. Okay, and when we use a chemical equation, that needs to be in units of moles. So nothing about this allows me to make a fair comparison. So that's where I would go through and look at the rest of the calculations. Poor formatting, moles of copper wire that reacted during the reaction. Well, if we set this up as I have you do it in class, I want moles of copper. Well, what do I know about my copper? I know the grams of copper. I'll place that in the numerator. Y, substance, substance, keep them both in the numerator. I would need some kind of conversion. That conversion would need grams of copper in the denominator, so that the grams of copper would cancel, and I would need moles of copper in the numerator. Where do I find that conversion? That conversion comes from the periodic table. That's a mass to mole relationship. Okay. I would then go through and do that in question B, which is now doing the silver. Okay. And then question C is now how many moles of silver nitrate were used during the reaction. That becomes a little bit more challenging, because what we have now are moles of copper and moles of silver. Okay. We don't have silver nitrate. To figure out the silver nitrate, I need a new conversion factor. That conversion factor comes from how I convert copper to silver, which would be a balanced chemical reaction. That balanced chemical reaction is in our given information. Sorry for the scroll. All the way up at the top, we would then see the relationship between our silver nitrate and our silver is 2 to 2. So I now have my mole conversion. I can now get moles of silver nitrate. Okay. With that conversion, I can answer that question. Sorry again for the scroll. And now they're going through and saying, what are all of those individual relationships? Okay. So A gave you moles of copper, B gave you moles of silver, C gives you moles of silver nitrate. Now we want each of those ratios. So the moles of copper to the moles of copper will be 1, because it's the same number. And then each of these are now going to be a calculation. Okay. After that, they're now asking you to come up with those relationships and start running some theoretical yield calculations and other kind of fun stuff. Okay. So hopefully that gives you at least a baseline to get started with that, as about a 10-minute summary, which I think is better than I did the first time. And I think I got about the same distance away. So I'm going to go ahead and pause the recording for that.